Good morning, students. Let us continue the current voltage characteristics in this video session. In the last lecture, we concluded that this is the drain current for MOSFET in triode region. This triode region, you also call it as linear region. Okay. So now, when MOSFET working in triode region, if you face this particular condition, if drain to source voltage is very less than gate voltage minus threshold voltage, what will happen? So automatically you can ignore this particular term of VDS square. Okay, if you ignore this particular term, the drain current will be approximately equivalent to this mu n cox w by L into VGS minus VTH into VDS. Okay, this is the resultant equation if drain to source voltage is very less when compared to this particular overdrive voltage. Okay. So from this what you can conclude means just observe this equation. Okay, so you know that resistance is equal to voltage divided by current. So bring this drain current in the left hand side to the right hand side. So VDS divided by ID equal to, bring the remaining terms to this left hand side. So the resultant equation becomes resistance, which is nothing but linear resistance, which is equal to 1 divided by mu n cox w by L into VGS minus VTH. So now this drain current is a function of linear function of drain source voltage. So from this what can you conclude means a MOSFET can operate as a resistor whose value is controlled by this overdrive voltage. Observe this diagram. Source, drain. This MOSFET acts as a resistance which is controlled by means of the gate source voltage. So a variable resistor. Are you able to understand the concept? A MOSFET can operate as a linear resistor when this particular drain to source voltage is very less when compared to the overdrive voltage. Okay, then what is the next step? So now keeping this in mind, now what you are going to do means now you increase your drain to source voltage, okay, greater than gate to source voltage. Okay, so what will happen? See, observe this diagram. Now you are increasing this drain to source voltage greater than gate to source voltage. So this is your first value and this one second value and this one third value. So after this particular limit, this particular drain current, it won't follow this parabolic behavior. So after this, it becomes drain current will get saturated and becomes constant. So now you can say that this particular device operates in the saturation region. That means the drain current gets saturated if the drain to source voltage gets increased above gate to source voltage. Okay, see this. Now after that also what I am doing is I am increasing this drain to source voltage further. So what will happen? See, observe this particular inversion layer. This is the inversion layer. This inversion layer, what it will do means it will stop at this particular point x, which may be less than or equal to L. L denotes the channel length, and now the channel gets pinched off. Are you able to understand the concept? This is the inversion layer. This inversion layer stops at particular point x, which may be less than or equal to channel length, and at this condition you say that the channel gets pinched off. Channel gets pinched off means what is the meaning means at this particular point the charge density drops to 0. Okay, are you able to understand? Now the channel gets pinched off. Okay, now further what I am going to do is further I am going to increase the drain to source voltage and I am going to see what happens in this particular inversion layer. See, now I am increasing this particular drain to source voltage further. Okay, now I am going to observe this particular point at which the charge density gets 0. So the point at which this particular charge density equals to 0 gradually moves towards the source from drain. That means what is the meaning means the local potential difference or voltage between this particular gate and oxide silicon interface, it is not sufficient to support inversion layer at this particular region. So what happens to this channel length? The channel length decreases from L to L dash. Are you able to understand the concept? The channel gets decreased from L to L dash. See, once again I will repeat. What I am doing means after the channel, that means the charge density at this particular point equals to 0, further I am increasing the drain to source voltage. Okay, so what will happen means the voltage between the gate and this particular oxide silicon interference is not sufficient to support this inversion layer. So what it will do means this point will start moving from drain towards source. So what will happen? The channel length will get reduced from here L to L dash. So the channel length decreases from L to L dash. So now I should reduce equation for this particular condition. So I am integrating this drain current equation with the limit from x equal to 0 to x equal to L dash instead of x equal to 0 to x equal to L, and on the right hand side V of x equal to 0 to V of x equal to VGS minus VTH instead of V equal to 0 to VDS, which results in this particular drain current equation ID equal to half mu n COX W divided by L dash multiplied by VGS minus VTH whole square. So this is my resultant drain current for the reduced channel length L dash. Okay, are you able to understand the concept? So now what I am going to do is I am going to deduce the equation for P MOSFET instead of N MOSFET. So now I can write the drain current equation as ID equal to minus mu P COX W by L multiplied by VGS minus VTH into VDS minus half VDS square. This is my drain current equation for a PMOS transistor operating in triode region. Okay. Then next one in saturation, what will happen? Drain current equal to minus 1 by 2 mu P COX W by L dash into VGS minus VTH whole square. This is my drain current equation when the transistor follows the pinch off behavior. You will understand the concept? Same equation for PMOS transistor, but the mobility instead of mu n, here I am replacing by mu p. Okay, you will understand? Okay. So next we'll move on to next topic. Okay, now you consider that MOSFET operating in saturation region. Okay, so this MOSFET, particularly when operating in saturation region, it will produce current. What is the output current? Drain current is your output current. Okay, what is your input voltage? Input voltage is gate source voltage. So this particular MOSFET operating in saturation region, it will produce current in response to gate source overdrive voltage. Okay, so the saturated MOSFET, you can consider it as a current source which is connected between drain and source. So from this you can derive one factor and you call it as transconductance. So transconductance, you normally express it as change in drain current, ratio of change in drain current with respect to change in gate source voltage when drain to source voltage is kept constant. So transconductance term indirectly represents the sensitivity of the device. How it represents the sensitivity of device means, if the value of this transconductance is high, what will happen means, if you produce a small change in this gate to source voltage, it will produce large change in drain current. Similarly, if the value of transconductance is low, a small change in gate to source voltage, it will produce only small change in drain current. So you can express this particular transconductance as the sensitivity factor. Okay. Okay, students, thank you.